Today, I am pleased to introduce today's session, A Table is Worth 1,000 Words, and our guest speaker here, Stefan Webb. Stefan is a developer advocate at Zillow, where he advocates for open source vector database Milvus. Prior to this, he spent 3 years in the industry as an applied ML researcher at Twitter and Meta, collaborating with product teams to tackle their most complex challenges. Stefan holds a PhD from the University of Oxford, where he has published papers at prestigious machine learning conferences such as NeurIPS, ICLR, and ICML. He is passionate about generative AI and is eager to leverage his deep technical expertise to contribute to the open source community and to you all. So welcome, Stefan.
Yeah, thanks so much, Sachi. Thanks for the kind introduction. And thanks everyone for being here. So I'm going to go ahead and share my slides. Okay, can everyone see my screen okay? Perfect. Well,
yes.
Before we get started, so I just wanted to say, feel free, don't be shy. If you have a question, write your question in the chat at any time, and I'll try and answer them as they come up. So thanks again for being here. The topic for today's webinar is foundation models for tabular data, or to make it sort of a bit more interesting, I'm calling it one table equals 1,000 words. In that, we'll investigate a recently developed foundation model that allows you to use a table in a more sort of like direct way than you may be used to with just standard large language models. So a bit about myself. So my name is Stefan, and as Sachi mentioned, I'm a developer advocate with Zillow, especially for the open source Milvus. So Zillow is the company behind Milvus, although Milvus has been donated to the Linux Foundation for AI and data science. My role as developer advocate for Milvus is, amongst other things, to help make connections or bridge the divide between the developers and the technical side and users like yourself. So that means I'm here to provide technical support, help you solve your problems to get Milvus into production, direct you to the right resource if necessary. Encourage you to connect with me on LinkedIn. Always happy to get a direct message, hear about what you're building. And also join our Discord, where I'm active with our other DevRels in answering user questions. So with that, let's get started. So before we get started, I wanted to tell you a bit about Milvus. So Milvus is the leading open source vector database. What is a vector database? For those who don't know, it's a special type of database that's designed to store, index, and search vectors. And typically these vectors are embeddings from neural networks. So it might be the embedding of an image or the embedding of a piece of text, or in our case, it might be the embedding for a table. And so the reason why we need these special databases is because embeddings, essentially, they're just like points in really high dimensional space. And so a traditional database just doesn't have the facilities to do efficient search. We need special algorithms, special data structures, special systems design considerations when we're designing a system specifically for vectors at scale. And so Milvus is the leading open source vector database, which is high performance. Really, like one of its sort of key advantages, I believe, is its scalability. up into the scale of like billions of vectors in production. And we have a very large open source community. So we have, we've had over 400 contributors. We're up to 32,000 stars on GitHub. The Docker pools in the tens of millions. So it gives you a sense of like how many deployments are out there. So we'll be talking a bit more about that and how it relates to these foundation models for tabular data. So another thing about Milvus is it's trusted by some of the some of the biggest companies that you know in tech and just like other industries. So it's everyone from NVIDIA to Roblox, Salesforce, Airbnb, AT&T, Microsoft. So that's sort of like, I think, a strong testimony that they're using this open source software in production and it's producing lots of value for them. So Milvus, it's designed for scalability, but it has a few different deployment options. So when you're prototyping, you probably don't want to be scaling up. You're not really still thinking about scaling up to the hundreds of millions or billions of vectors yet. So we have a version called Milvus Lite. You can run it in your Jupyter notebook without any sort of starting a server, and locally hosted. Use that very easily for prototyping. Then there's like one step up from that is a standalone version, which runs in a Docker image. It has more of the like advanced search algorithms for like a small deployment. This is perfectly fine in the tens of millions of vectors. And then finally, Milvus cluster is a fully distributed system working across tens to hundreds of nodes and scales into the billions of vectors while maintaining that really high performance under 100 millisecond query latency. And so being open source, Milvus integrates with the open source ecosystem really nicely. And so pretty much like every major tooling of the generative AI ecosystem, whether that's open source or closed source, there will be an integration with Milvus. So everything from Hugging Face, LangChain, OpenAI, Llama Index, Ragus to Airbyte, Gina AI, etc. And so as mentioned, so the reason why we need these special vector databases is because a traditional database is just not designed for storing neural network embeddings. A standard relational database, for example, doesn't have special features for indexing and searching high-dimensional spaces. But even if one of these databases were, as they have, to add these features, they're not designed from the ground up for scaling. So that's sort of why it makes sense to like look at solutions that are designed from the get-go to work with vector embeddings. And so just before we get into like the topic for today, I just wanted to mention one new feature from the latest version of Milvus 2.5. And that is that we've added the ability to do lexical search. So lexical search is more of like a traditional type search that's based on keywords, whereas typically with a vector database, you'd be interested in semantic search, which is based on these neural network embeddings. So we've added this feature so that you can do lexical search and you can actually combine that with your semantic search. You can have like a hybrid search and get the best of both worlds. So you can have your semantic search for like your sort of like fuzzy semantic matching. But then if you're depending on like precise keywords, then you can also return and combine results from a lexical search method. Okay, and just one more thing. So if you're sort of like thinking like, okay, why Milvus? I really encourage you. So check out the benchmarks. We have an open source suite of benchmarks in the link below, and that gives you a really good sense of its ability to scale and how that compares to other vector databases, both open and closed source. Okay, so that's sort of like a good segue into our topic for today, which is foundation models for tabular data. And I typically tell a story that goes a bit like this. So unstructured data is becoming more and more prevalent as time goes on. And so it's estimated by the end of this year, I think it's something like 80 or 90% of all data by size will be unstructured data. Now, what do we mean by unstructured data versus structured data? So my personal definition is unstructured data is data that doesn't have a readily available feature representation. And so it's the type of input that you necessarily need to put through a deep neural network to extract a representation of. And so that's things like text. So by itself, text is just a sequence of characters or words or tokens. So in a so when I say like it doesn't have any features really available, we can sort of like give each of those tokens or words an index from 0 to the size of the vocabulary, but that doesn't tell us anything about the relationship between words. So the word dog, that might be token 500. The token for hound might be, I don't know, 10,000. And so those words are obviously related in meaning, but to the algorithm, they're just two numbers with no relation. And so to extract like a representation that is more usable for machine learning, it's the sort of input that we need to put through a deep neural network that's been trained to extract representations or features. And so in contrast, by structured data, we mean things like, I think all of these entries I've got in the table on the left-hand side can be summed up as tabular data. So if you have like a column in a table that's say, age, that might be, you have 16, 42, 71. Those are numbers that have direct meaning, directly interpretable, as opposed to just like the numbers in the pixels of an image, for example. Or if you have like, maybe it's like a time series of temperature. So it might be like the time series of the temperature over the course of a day that's measured in Fahrenheit or Celsius, depending where you're from. So Celsius for me, I'm Australian originally. And but again, like that's something that's directly interpretable. That has like a direct sort of meaning, which is unlike the so for example, like an audio signal where each sample is just like a loudness, at that particular point in time. But it's sort of unclear like how does that relate to like what the sound is, how is it perceived? Is it like a dog barking or a human saying something? So we make these distinctions between these two types of data, structured and unstructured. And so the story that I typically tell is that unstructured data is becoming much more prevalent in the world. And so we need to get like the extract the meaning and the value out of it. We need to produce vector embeddings from it using deep neural networks that have been trained for this purpose. And then we have vectors. We can then, so you need some sort of like software to sort of conveniently store and search these. And so that sort of motivates like the importance of a vector database. And that's something that, once you've stored them, and then you can use them for all sorts of purposes downstream. So whether that's you're using it as like an external memory store to your retrieval augmented generation system, maybe like you're looking for duplicates, you're deduplicating your data set. So, you want to sort of search for similar entries in your vector space. Maybe you're just using it to directly find similar entries for like the top matches for a recommender system. Okay, so that's typically the story I tell. So I'm going to tell a slightly different story today. So the first story, that's still relevant, still very important. But so this sort of, I guess, sort of like a elaboration of that is that structured data, even though it has a representation that may be like readily available for machine learning algorithms, your your decision trees, your logistic regression, etc. It's still useful to treat it as if it were unstructured data in that it's useful to develop a neural network that you can put these structured inputs into to extract a vector representation, just like we do for language and text, and then use that in the same way that we do all the things that we do with deep neural network embeddings. And so why would you want to do that? So I think there's a few reasons. So firstly, it's just like a very powerful way of learning in an unsupervised or self-supervised way. So I think typically when you're doing a task with tabular data, you're probably sort of looking at a supervised classification or regression task. But what if we could just sort of learn from billions or even trillions of tables, sort of learn some knowledge from like all the tables in the world, and then transfer that across to a specific machine learning task for tables on hand. So we could use this to do zero-shot learning of tasks in the same way that we do zero-shot learning of language tasks with LLM. That's one thing. So a second reason is we may want to combine the tables with other modalities. For example, we might want to do a natural language search of our table. And that's not something you can do. Outside this framework of deep learning, that seems very difficult. But once you convert it into a vector embedding, then you're working within this generative AI world, and you can use all of like these well-designed ideas for working with multiple modalities. And in the same way that you can ask ChatGPT, ask it questions about images, ask it questions about videos. The hope is that we could also do that for this modality of tables. So that's kind of like the story for this webinar, is that it's useful to treat a table as an unstructured input for several reasons, so that we can bring tabular data within the generative AI paradigm and build it into RAG systems, the recommender systems, agents, all the other applications of generative AI foundation models. Okay, so just like one sort of really specific example. So I'm just sort of illustrating like a question answer application of a table. So the goal is that we can take a table in some representation and we have a query. And so the query is, among all science fiction series, which ones air after 8 p.m. and have a rating above 8.5? And the table, it looks like it's a table of science fiction movies it's got name, summary, average runtime, etc. So the hope is, or what we'll be talking about in this webinar, is some sort of like generative AI black magic that can then take those two inputs and do like answer questions, and with some sort of like understanding of the what's in the table. So some other applications you could see. So foundation models for tabular data, you could use that to summarize. You could give it a table and then say, maybe it's like, I don't know, like the quarterly statement, some sort of like time series based on the quarterly statements of a company. And you might say, okay, what are some key takeaways from this with regards to XYZ? Get it to sort of extract some insight from that. Table understanding. So maybe you have like a table, but one of the columns is missing or has been mislabeled. If this model can do table understanding, it should be able to automatically complete the table names. Or maybe it's just like a productivity tool. Like maybe when someone's designing a schema, maybe like it helps auto-complete the column name for the schema. So fact verification, a bit quite similar to question answering. Table to text generation. So I think there's a bit of like overlap between these, depending on how you see them. But the last one's a bit different. Maybe we could go from text to tables. Maybe we could say generate a table of let's see. So maybe you could look at populations across countries in a given time, produce a table with that data, and then maybe like it could be using some tools to like pull information off the web and then turn that into a table where it's synthesized the schema and populated that schema with the data from the web. So you can see that there's many sort of interesting and I think sort of potentially valuable applications of if we had a foundation model for tabular data, or applications of if we treat tabular data as an unstructured input. So in this presentation, I'll start off just by talking about some sort of general points about foundation models. And then I'll be looking in the second part on a specific architecture, so a specific paper that suggests a method for this. And so this talk is not sort of endorsing or saying like a specific paper is best or particular model is best. It's just to illustrate how these ideas might be done in practice and give you some actual libraries and models to work with afterwards. In the third section, I'll talk about the data, why that's important, where we might get it from. In the fourth part, I'll talk about agents and how this might fit into like a useful agentic framework. And then finally, I'll run through some code. So looking at the Python library from the authors of the paper that we'll be looking at, and showing some things that you can do with that. Okay, so the goal is that we want to be able to treat a table as unstructured data and bring it within our RAG systems, agents, etc. So the basic paradigm is going to be like this. So we have our table. We then we'll put our table through an encoder. So that's a neural network, but one that's been especially designed for tables. And so it will have some inductive biases built into the architecture specifically for tables. And those inductive biases will be things like if you sort of change the order of the rows or you change the order of the columns, that shouldn't change the representation of a cell. So similarly to how like for other inputs, we have models that have inductive biases built in. So you can think about convolutional neural networks for images is just one example. So we'll talk about some ideas for like a specialized type of transformer, which can take tables and then with some, because it has some specific inductive biases built in, learn really appropriate representations. And then separately, everything within the sort of like the shaded box, that's sort of something new that goes one step beyond like the standard LLM paradigm. So separately, you have your text, you tokenize that. So this might be like the question that you're asking of the table. And then, but we need, so we have like a table encoding, we have like a text string that will be encoded. We need some way to sort of like translate between the two. And so we'll be talking about this concept of a Q former, which is essentially just like a small model that's trained to translate between the table encoder representation and some special tokens to put into a combined prompt. And then after that, we just have like a standard prompt with tokens the large language model can understand. And then, from that, we can get out a response. So this is sort of like the paradigm that we're going to be using to accomplish this goal of developing a foundation model for tables. And so the specific paper or implementation I'll be talking about today is it's a paper by some researchers at Zhejiang University from late last year, and it's called Table GPT-2. And here's sort of like from a high level what their model looks like. So let's look at the table encoder to begin with. So it starts off the right-hand side. You have your table that might be coming from an Excel spreadsheet, relational database, etc. It's just rows and columns. We then put that directly into our table encoder. And our table encoder, it's sort of like a modified transformer encoder that you might know from language modeling and learning language representations. So, and a few sort of like differences that it has. So it uses this bidirectional attention. So in like when you're doing language modeling, there's only one dimension. There's, you can go left or right in the sentence. And so a given word is able to attend to all the words before it and all the words after it in an encoder. So, I mean, if it's like a causal attention, then it'll only be able to attend to the words that have already happened that are behind it. But for a table, for each cell, both the corresponding column and the corresponding row are relevant. And so each cell should be able to attend to its row and its column. And so that's why we've got, that's why they implement this bidimensional attention. And then from like a high level, like another thing they do is they sort of alternate between layers that ignore the positional encodings of rows or ignore the positional encoding of columns. And so that way they can sort of build in this invariance to changing the order of the columns or the rows. So the table encoder is like a modified language encoder, a transformer-based language encoder. So the table goes through there and is then output into some sort of like representation that the Q former. So this Q former is like a translator or an adapter. It can take the representation and then turn it into one of a number of like learnable queries. Combine that with the text prompt from the user to create like this hybrid prompt, and then the hybrid prompt can go straight into the large language model decoder directly. So So in that way, we're able to um, transfer all of the learning from a really massive large language model. Um, you know, uh, I'm sure like you've used like Llama 3, ChatGPT 4, et cetera. But we've done some additional learning on top to adapt it to input the modality of tables. And so this type of this type of modeling framework for multimodal embedding models is quite it's developed for other modalities too. So I think in the context of the original Q-former, I believe that was in the context of large language vision models. So instead of a table, just imagine you have like an image, you break the image up into patches, you then put it through your transformer architecture that's been specialized for image patches. You then have a Q-former that has been trained similarly to produce these learnable queries. And then you can just put that directly into the large language model decoder. So this is like a general paradigm. Presumably it would work for any other modality where you can develop an appropriate encoder, which depends on having the appropriate data plus the appropriate, way of building these inductive biases into the architecture. Okay, so this method, it's not entirely novel. It takes some existing ideas from large language vision models and then adapts them to tables. And so once you have that output, you can then, put that into your RAG system or your agentic workflow. It's just one part of the many different ways you could build a pipeline. Okay, so how is this model or these number of models trained? So like many other systems you will have seen in generative AI, it's not trained end to end. It has several discrete training steps where we train or we pre-train parts of the model individually. And so in the case of Table GPT-2, they start off with the Quen 2.5 large language foundation model. And so that's already been trained on, I think, like tens of trillions of high quality tokens. So that's been pre-trained. Then they do some more pre-training of that model, but specialized on. So I think that they use like some data from textbooks that may be relevant to business intelligent tasks. So they're just doing like a bit of additional pre-training to try and like specialize Quen 2.5 for business intelligence, because the presumption is that if you're working with tables, you're most likely going to be looking at business intelligent type tasks. And then they do a supervised fine tuning after that on some specific business intelligent. So now they've got like labels that they're doing some supervised fine tuning. Separately, we have to train the table encoder. And so in the same way that Quen 2.5, it's not a blank slate. It's been trained on, tens of trillions of tokens. We need to pre-train our table encoder, but we are starting from a blank slate. So we have to take this sort of blank model and then train it perhaps similarly to how a large language model is pre-trained. But in this case, what they do is they do contrastive learning. So they do this form of self-supervised learning on like a really large data set of tables. And for those of you who don't know, so contrastive learning, what that means is the objective is for the model to embed related items. They should have they should have an embedding that's close to each other, whereas unrelated items, their representations or their embeddings should be pushed further away. And so column-wise, I forget the exact details, but I think it's sort of like knocking out some columns at each time point. So it's yeah, so sort of like a self-supervised type of learning where it's learning to assign a representation to tables for cells that have a similar context. And then after that, then there's these 3 steps. The orange box, that's the encoder. The green box, that represents this Q-former translator. And then the blue box, that's the large language model. So these 3 steps here, it's just the process of how we go from taking like this pre-trained table encoder and then learn to translate between that encoding and the token language of the large language model. And so once we've done that, then we have a table encoder that can output tokens that are understood by the large language model. And then there's this final step of preference learning. So you might call that like instruct or instruction tuning, a specific method. So I think in this paper, they're using what's called direct preference optimization, which is a standard method you'll be able to find in all of your fine tuning libraries. So this step is just to fine tune the Q-former, the translator, to some synthetic data that they've constructed for this purpose. So maybe just a few other things. So Quen 2.5. So one of the like specific goals of this model is that it will output code that will enable you to query your table to answer a question. So you have like a table, you ask it a question. We want to be able to output Python code that you can then run that answers the query. And so this continual pre-training, in addition to like the training on textbooks, they also train on a large amount of code, both from Stack Overflow and GitHub. So there's some specialization for coding going on as well. I think one of the challenges of this method is the authors. So there's standard large or massive data sets for large language models. You can download curated crawls of the web. For tables and for many other modalities, there's no such data set that exists. So I think like an initial challenge is just to get the data that you can then train this model on. And there's only sort of, as we sort of like found out with large language models, they sort of obey these, predictable scaling laws in compute and data size. So we understand with this that if we actually want to be able to produce a useful model that is robust to answering all sorts of queries, we need to really collect as much data as we can. Like this is going to be one of the most important components to make this work. And so what the authors do of Table GPT-2 is, because they sort of hypothesized that for business applications or business intelligence applications, coding is going to be so important. So you can just imagine like like a consultant or a data analyst. They've got some sort of question about business metrics, and so they'll need to write like a query in SQL or some statistical language, or maybe even Python to answer that. So our model should be able to do the same. And so, as I mentioned, they get massive amounts of coding data from Stack Overflow and GitHub. They then have some general textbook data from finance, maths, biology, etc. And then for another part of the pipeline, they actually have some supervised data from Kaggle. Then I think there's like some smaller open source question answering data sets on tables. So they just like, put in all of those. And then they also have a lot of synthetically generated question answer entries, which are then sort of like refined by, I guess sort of like vetting by human evaluators, and then like using that to sort of like sort of continually like refine a set of these synthetically generated question answer pairs. Okay. So there's other important parts of the data pipeline. So we can collect all of this data, but more is not necessarily more. So I guess like another lesson we've learned from large language models is that it really matters like data quality. And so after collecting this data, they do a lot of data curation. And so whether that's like filtering, so removing duplicates, removing whatever might be considered like a, like a low quality entry in the context of that particular part of the pipeline. Cleaning, so maybe some table has missing values, removing that. Also, augmentation. So they have some methods to augment given data entries, and so whether that's by like sort of like it might be, for example, by changing like the wording of a question or a query, making, maybe it's like adding some noise to the table. So data augmentation, in the same way that we do for image models, is like a powerful method to make it more robust to whatever the input is. And so for tabular data, they collect data from all sorts of sources. So they look at, so I think primarily from like a web crawl. That's where they get most of this tabular data from, but also from research data sets, and some other sort of like publicly available sources. So basically, they're just like going all out and finding as much tabular data from any source possible, and then doing some curation on that to improve its quality. Okay, so let's talk about like how this might be used in an agentic workflow. So imagine we now have, so this is like a particular agentic workflow that they suggest in their paper, and that is implemented in their Python library that we'll take a look at in a second. Just say, so you start off with like a table, and you want to ask some questions of that table. Firstly, you need to prepare your inputs, and that involves normalizing the tables. So they found that for the table encoder to be effective, the representation of the tables has to follow, has to have like a normalized format. So you can think about many tables, they have like merged cells, maybe just like blank columns, etc. So they have like a simple algorithm to normalize that. And then we may want to do like at this point, look up our vector database for some relevant knowledge to provide the context to our large language model, depending on what the query is. And so then, so we put our prompt with the table encoding, as well as any additional information we've got from our vector database into the table GPT-2, and then it will output Python code. And then this agent, it can then execute that Python code in a sandbox. And then it can either, either just return the results. You may optionally put it through a large language vision model to turn that into like an image, or like a plot, if you will. And then, yeah, so, you can either sort of keep chatting with your large language model, or, you can just sort of take those answers as is, and, that's your response from the system. But one of the things about this agentic workflow is that it will sort of like reflect on the results and try and look for any errors. And so it might have like multiple iterations of this generating code, running it, observing the output, reflecting on that, modifying the prompt, modifying the Python code, doing the same thing until it's satisfied with the output that it gives. And so this is the exact prompt that they use in their code. So it's this table GPT library. So you are table GPT, an expert Python data analyst. Your job is to help users analyze data sets by writing Python code. Each markdown code block you write will be executed in an IPython environment. So this is just like defining the parameters of the agent and how we want the output to be, what are the constraints on the input. So we give it some conditions to say things like, as part of your output, you can call this function read_df to read different file formats. So that's like a given. If error has occurred, try to fix it. So that sort of feeds into this, like this sort of like this reflection feedback loop. Okay, so yeah, and so the system is sort of like a a demonstration of a useful agentic workflow for working with tables in natural language. So very quickly, let's actually look at some code. So I'm going to let me just log in. So let's look at some code here very quickly. So the authors of this model, they provide the sort of fine-tuned language model via Hugging Face. They haven't yet made the weights for the table encoder publicly available. So we can only really sort of like test part of this pipeline. But this is like an area that's rapidly developing. So just sort of project ahead, say 3 to 6 months, there will be several open source table foundation models, and it's just going to be like a standard tool that you use. So in this example, we'll just sort of like see what happens when we query the large language model directly rather than go through like a agentic workflow. So we've got like a spreadsheet encoded in the string. We then load our model from Hugging Face, just using the standard auto model call. And then we have a question, which they say that it sort of works better questions in Chinese, but it also works for English too, as I found out. So we'll just go down here. So we're going to say the question is, which games have a record of 40 wins and losses? And then I've created this helper function that actually turns that into a prompt and then calls the large language model, generates the output etc. So we've got this spreadsheet. So we've put in a table, we ask it a question, and here's some of the output. So it then takes that and generates this Python code, which very clearly like it's doing what we want it to. But what about some other questions? What about for which game does the team lose by the most points? So then again, looking at the output, it seems like this is working too. It's looking at this difference. This is looking at the ID of the maximum point difference. So it's able to do a query like that. Maybe like a more complicated one for each team, sum the number of points by which they lost across all games. It can then turn this into Python code where it sort of knows to do a group by. So it's able to compose more advanced queries as well. Uh, this might be something that you can already do to some extent with like an out-of-the-box large language model. But with a model that's been specifically fine-tuned for this purpose, has like a specialized encoder. They show in the paper that they really sort of excel in the benchmarks. So I think Sachi's come in. I think we might be coming up to time.
Yes.
Uh,
We
yeah.
sorry to
So,
bother, sorry to interrupt here. We have about 5 minutes left, so we have a few questions. Is it okay if we go ahead and answer those right now?
yeah. Let's go ahead and answer those. And I'm just gonna let's go ahead and answer the questions.
Okay, great. So one question is it's just a clarifying question. So they're asking contrastive contrastive learning is just like ML where they're trained on different types of data like for and adverse to the topic.
So um yeah, okay. Um uh so I think that statement could be interpreted in several ways. Let me just clarify. So contrastive learning, it's a type of learning where we maybe like it's easier to understand in the context of language models. Say you're learning an encoder for sentences. Then, so how contrastive learning works is you take a batch of examples. So maybe you have like, I don't know, 10,000 examples. And for each input, you have a corresponding output. So the input might be the dog. Why is the dog barking? Or what sound does a dog barking make? And then the output, something related. So when we encode that input and output, the learning function, it drives those two representations closer together. Whereas for every other example in that batch, which is unrelated, the objective will push the encoding of that input away from the other ones. And so that's contrastive learning. So that's different from preference optimization, which we do in generative AI, which is for each input, we say, okay, here's one potential output, here's another one. The model should prefer this one over that one. So that's something separate. Don't get that confused. Hopefully that clarifies what contrastive learning is.
Yeah, it looks like they followed up by saying they're talking about weights in ML. I'm not sure if that
Um,
relates.
yeah, sure. So this objective, it's learning over, gradient descent over the weights of the encoder. And so um, uh, what I was describing was like the loss function. And so by, just like standard deep learning, with this given loss function, taking gradient descent over the weights, then we sort of, this learning happens on the weights of the model.
Okay, thank you. And feel free to follow up with Stefan if you have a follow-up to that.
Yeah.
So another question is, what is the use of biology in the implementation? Can you explain?
Yeah, sure. So um, uh, I think, yeah, so it may not be like immediately clear like how so this model sort of like they're aiming it at business intelligence applications. So how does like biology fit in? So I mean, I think it's sort of uh I think they were just trying to give it like a breadth of scientific knowledge. And so I guess they sort of, took biology to be like one of within that remit. So I can't say for certain like how useful is table analysis in biology. I'm not sure about that. But it seems like just sort of giving it like a breadth of scientific knowledge is like a reasonable thing to do.
Okay, thank you. And one last question. Is there any particular normalization form, like so they put in parentheses NF1, NF2, NF3, in which our vector table to be used in MILDIS?
Yeah, sure. So if I understand the question correctly, so firstly, so they haven't made the table encoder publicly available yet. So you can't yet sort of like use that part of the pipeline in your application, but I think it's in the next couple of months, it'll be released. There'll be several models available in 6 months from other companies and research groups. So there's the table normalization that happens uh, as the input to the table encoder. I think in terms of like how they sort of process that, dealt with like merge cells. I would just check the paper for more details, and it'll go through like the specific details there. Yeah, refer to the table GPT-2 paper for more details on that.
Okay, thank you so much. And Mayang, you were the one with questions about biology and the use case. So if you have follow-ups, Stefan also
Mm.
does office hours. So you can get any additional questions answered there. You can also connect with him on LinkedIn. So thank you so much for all your questions. And we are at time for now. So please come to our upcoming webinars, which we have in the chat. And we'll see you at a future webinar. Thank you so much, Stefan, and for the participants today.
Yeah, thanks, Archie, and thanks everyone for attending today. And hope to hear from you and see you at our meetups and webinars.